Welcome back. We are still talking about our favorite equation so far. A x naught plus E. But today we're going to consider the case where E isn't some given error, but E is actually random noise. Now, as we were doing this before, you were probably already thinking ahead. Of course it's going to be random noise, but we didn't do statistical analysis per se, except to look at what the average error would be over all possible values of E, assuming that all were chosen equally. But here we are going to explicitly assume that E is random. And so what this does is it takes us now to a point where we're not trying to estimate the best solution for a given set of data. We're trying to come up with the best solution statistically. And the differences are subtle but important. So, a few things about E. We're going to assume that our error is zero mean. And we're going to assume that we know our correlation matrix to be R. Okay. Given all that, what is the best statistical estimate of x naught? Okay, we're going to impose a few constraints. One, the first constraint is going to be linearity. So that means that for some matrix L, where L is in R and by M, we have that x naught hat is equal to L times Y. Okay, so we're only going to look at solutions of that form for now. Two, we want our estimate to be unbiased. Unbiased doesn't necessarily mean best, but it is a nice constraint to make sure that our solution behaves well. So that means that the expected value of x naught or x hat has got to be equal to x naught. And equivalently, that means that x naught hat minus x naught, that difference is the zero vector. Okay, next. Use of the word best. I don't know if you notice the title. Our title up here was Best Linear Unbiased Estimator. Having grown up speaking English, I would probably have said Best Unbiased Linear Estimator. It would have made more sense in this particular case. But the nice thing about Best Unbiased Linear Estimator, or Best Linear Unbiased Estimator, is that it has this really nice acronym, BLUE. So why am I writing all this in black ink? I'm not sure. Maybe I should change. Okay, so these are the constraints that we're going to follow. Let's come down, and I'm going to drop the, I know I can put it in there. We've got this, and we know that this is equal to L times A x naught plus our random vector E, and which is of course LAX, one of my least favorite airports, plus LE. So if we want this to be unbiased, this is a constraint we can bring in here to simplify our problem a little bit. We're going to have x naught hat minus x naught. It's going to be L A x naught. This is part of our estimate from up above. Now here we're going to have plus the expected value of L times E, and now minus the expected value of x naught, but since x naught is a given and not a random quantity, we get that. And we need this to be equal to 0. Well, first off, since the expected value of E is 0, the expected value of L times E must also be 0. The expectation can flow through, so we just have L times the expected value of E, which is 0. And so that comes out, and that tells us that LA x naught has got to equal x naught. So in other words, L is the left inverse of A, or in other words, LA is equal to I. Okay, requirement number 1. Let's put a big green box around that. There we go. So we've now checked off the linearity. We assumed we had a linear estimator. So I guess we could put that right here. Unbiased. Unbiased gave us this constraint on L. The L has to be the left inverse of A. And now let's do best. For the best, we need to minimize the expected value of x naught hat minus x naught, oops, that should have been blue, squared. Well, we're just going to have a little bit of algebra for a moment here as we put everything out. That'll give us x naught minus LA x naught minus L times E. You might have noticed that I just multiplied everything in there by -1. It's a little mistake on my point, but it's still valid because we're squaring it. Well, what do we know about this? We already know that this quantity right here is equal to 0. We found that that had to be true for our unbiased requirement. So this simplifies down to just the expected value of the norm squared of L times E, and we just need to find L to minimize that. Find L. Okay, so let's solve this. We want to find the minimum over L, subject to these constraints. L E norm squared. There, that's our goal. What is norm squared of L times E? That would be equal to that transpose, so E transpose L E. Well, this is going to be a bunch of terms put together, which is basically going to be L Okay, let me start this explanation again. We have this quantity here, and we're not quite sure what to do with it. We know what the expectation of E times E transpose is, but not what E transpose L E is. So is there a way we can rearrange things? And the answer is yes, there is. Let's first take a look, a little aside here. Now what happens when we have a vector, say v, and we have, it's a column vector, and we'll just say it's equal to v1, v2. So with v transpose, we're going to get v1, v2, v1, v2 is going to be v1 squared, v1, v2, v2, v1, and v2 squared. On the other hand, if we had v transpose v, we would just have v1, v2 times the column vector, and we would get v1 squared plus v2 squared. Well, notice that we have all those in our outer product just sitting there on the diagonal. And although this is just a demonstration and not a proof, in general, it is true that in general that v transpose v is equal to the trace of V transpose. Okay, so that's a starting point. There's one other thing we need to do on our little aside to figure out how to simplify this, and that is note that some matrix times a vector times same thing transposed is equal to, actually let's do the expectation here, because we're going to be doing that. That'll just simplify our whole approach. Is going to be equal to the expectation of V transpose M. So if V is a random vector, as is our E vector in this case, that's just going to equal M expected value of V transpose M transpose, which would be M RV M transpose. Okay, so we're going to combine both of those properties together. And scoot this over so I have more room to work. That lets us write this as the minimum over L, where L is an n by m matrix, and L is the left inverse of I, of the trace of L R L transpose. So the solution is L naught is equal to A transpose R inverse A, all inverse A transpose R to negative 1. So this is our best linear unbiased estimator, and in the next video we will check that.